Okay, next up, actually I got I guess I'm lucky to have John McHugh on my session because he doesn't really need an introduction because you've all been hearing him most of the week. So he is the chief analyst and senior principal at Red Jack, but you know him as the guy that's always at the other microphone. So now he's got the main one.
Okay, so I can probably take as well as I give, line up. All right, let's see, what do we do to fly this machine? Probably press a button here. Okay, we'll talk about the landscape. What we're going to do is revisit some of the things that we've done for storing flow data, and we've just heard one talk, and actually it has a lot in common with some of the things I'm going to say, and I think you can pick out the similarities. But we decided as an experiment to try putting the data into Amazon's Redshift data warehousing system. And we've got some preliminary results, and we've got some ideas for things that might make it better, and we'll talk a little bit about the possible future things to do. Okay, very early on in Silk development, we experimented with relational databases as a possible repository. At that time, it didn't really work at all. The storage requirements went up by a factor of 10 or more. Response time and cost went up as well, and it looked like an all the way around losing proposition. So we chose to go with flat hourly files and Unix-like command tools, and as needs evolved, parallel architectures for doing this were rolled, and that's where it sits now for the most part. But a lot of things have changed since the early 2000s, and it might be time to revisit some of the decisions. They were definitely right then. The question is, are they right now? This all started when it became possible to rent a server in a lights-out center for a small amount of dollars per month. And that makes a very nice economic argument against building your own data center, having the physical security, electricity, et cetera, on that. Now, these things started out as physical machines, but pretty soon they were virtual boxes, and this repeats the cycle that we've seen over and over again of going from a single-use machine to multiple use, back to a cheaper single-use machine, but then that got powerful enough to do multiple use, and so on. And now we're seeing big platforms with dozens of virtual machines running on them, and probably we're going to see virtual machines running inside of virtual machines fairly soon as another way to slice the pie even thinner. Now we've got cloud providers such as Amazon, which basically is a money-losing bookseller located in a town north of here, that offers a wide variety of computing services off in Never Never Land. Redshift is a data warehousing service. It looks a lot like Centaur if you strip away a lot of things. You've got data clustered and accessed through things. Basically, a lot of the operations are sequential searches of the database. Even if it doesn't do flow well, it might teach us things that would make Centaur better, and Lord knows Centaur could use it these days. So Redshift is not quite a full-blown relational database. You store stuff there, but you transform it in Redshift at your peril, because that's a very expensive operation with data garbage collection problems and related sort of things like that. It's more like a roach motel. The data checks in, it never checks out. Deletions can be hard, but it fits with the data storage mentality that we have for a lot of our analytics, which is never throw anything away. It well fits the store once, query many times model that ought to characterize a lot of the analysis we do. It can support single or multiple tables, but if multiple tables have the same structure, there are a lot of advantages to combining them into a common view. Among other things, this can solve the deletion problem if data becomes stale and is timed out. So if we say we want to retain data for a period of 3 years, we could have daily tables for 3 years. That's only about 1,000 tables. And every day we could discard a table and add a new table and reconstitute the view so that the remaining tables are there along with the new one. This is sort of like what you get when you say in Silk to RW filter flow type equals all. You're glomming together all of the partitions that you have created and creating views that contain all of the data. Redshift stores its data in blocks of about a megabyte. It reads whole blocks into memory and processes them there. Within a block, it's a columnar store. So data from a given column is stored together. One of the things that this does is, because data in a column has a lot of the same characteristics, you can get really good compression. And you can pick compression that is good for the particular block. For example, if you have a column of Booleans, just 0 and 1 values, if there happen to be long runs of either zeros or ones, run length compression is really, really good. Now, if it happens to be that the values run 0, 1, 1, 1, 0, 0, 3 zeros, 4 zeros, ones, and so on, that compression is not good, but there are other compressions that are really good for that. So Redshift does a good bit of analysis of the columns before it decides how to compress them, and then picks things that appear to be optimal for what you're doing. Another thing that you can do is ignore columns not in the query. So if you know where in the block each column starts, you don't have to even decompress the blocks that you're not concerned with, and that's a real plus. On the other hand, select star is a bad thing to do, and we'll see some timings that show that. But we had some experience doing an evaluation of SenseAge's system, and select star was the thing that absolutely killed it in terms of performance. It just doesn't work. Okay, data is stored in a single sort order. The blocks are ordered. Okay. You know the minimum and maximum key for the block. So if you can answer your query in the negative, i.e. this block couldn't possibly have any data that involves this query, you don't have to go any further than to look at the min-max key for the block. You don't have to read it into memory, you don't have to unpack it, and so on. So that's a real win if you can access the data in that way. Depending on what kind of nodes you use, you can get anywhere from 1 to 32 nodes in the database, or 2 to 128 nodes in the database. And this provides for parallel query execution, especially if you've got logically a single table, everything is looking the same, you can run the query in up to 128 parts in parallel. This makes the serial passing of the database a bit more palatable than it might be. But there's no such thing as a free lunch. It's cheap and easy to get started. In fact, it can be very cheap. You can play with it for up to 3 months with up to 750 node hours for nothing. DW2 large nodes, which give you 160 gigabytes of SSD and about 15 gigs of RAM, I think, per node. I think you get 2 virtual cores per node. Costs 25 cents an hour on demand. So if you want to play with it for a while, that could be fairly cheap. My 16-node cluster that I used for the large data sample costs $4 an hour to run. That's about $100 a day. You wouldn't want to leave it idle for a year, but you can spin it up in less than an hour and do some stuff on it and then put it back down. There's no cost when you shut down, but you pay S3 storage rates for the snapshot. So, you can keep your data offline for less than you can keep it online. If you're going to use productions, you basically want a 3-year contract. The DW1s, which go up to 16 terabytes of disk per node, are $1,000 a year per terabyte on a 3-year contract. The upper limit on DW1 is about 2 petabytes on 128 nodes. That'd be around $2 million a year to do that. Now, that's no capital expenditure for those 128 nodes and their associated 2 petabytes of disk. No maintenance staff cost, no nothing of that sort. So compared to running a cluster of that type on your own and replacing the equipment every 2 or 3 years as it becomes obsolete, that $2 million a year may be chicken feed, or it may be significant. What we're currently experimenting with are 1, 4, and 16 node DW2 large clusters. So those are, towards the bottom end of the scale. What we did for the table design was a flat table like Silk Records, a time series of tables at the rate of 1 table per month. The fields are start hour, which is basically the start time of the data within that hour with the minutes, seconds, and hours, minutes, and seconds truncated off and set to 0. Source and destination IP, prototype, start and end time, duration, ports, ICMP type and code, flags. We put all the 12 possible flags, including the 3 unallocated ones, in because sometimes those show up and sometimes they're interesting. That's something you can't see in Silk in the current versions as far as I can tell. We have separate flags for initial flags and sessions and actually for the full flags as well. We have the Silk status flags for continuations and so on. We have a couple of linkages. We have the start time for the reverse record if there is a reverse record. We have the prototype for the reverse record if there is a reverse record. With fine enough time granularity, that should be sufficient to uniquely identify the matching record, and so we basically have put back together the ability to get back to the biflows cheaply. For continuations, we have the start time of parent and child. And then we have a sensor ID. Now, the interesting thing about these linkage fields is if they're empty, they're very inexpensive. And so that's an example of a column which could be very, very sparse. We have very, very few continuation records where the record had an active timeout and continued. But when we have them, it's nice to be able to put the whole chain together. And you can do this by using the linkages when you find one and going forward and backwards to find it. The sort key is start hour, source address, protocol, and start time. And actually, start time shouldn't be on there because we've never seen a case in the experiments we've done where there were multiple records that were differentiated only by that start time. And it's not going to show up when you get down into the block indexing as something significant. The use of start hour allows hourly appends of sorted data to an existing table. And that's important because if you add data in sort key order so that the key for the data you are adding is greater than any key that's in the table already, it's a very low-cost addition. If you add keys that are already in the data, they have to be shuffled in because the data is maintained in sort order. That means you wind up doing an expensive process called vacuuming the table to get rid of the records, the empty spots that were created when you munge things around, which is why you don't want to munge things around. We're using SQL Workbench to interact with Redshift. Queries are formatted on the local workstation. In this case, it was my MacBook Pro, sent over the network to the Redshift cluster. The results are returned to the workbench and presented on the screen. You get some slight differences in timing when you looked on the AWS console for this thing and what you get on the SQL workbench. But we use the timings from the workbench because they're easier to record. And we're talking fractions of a second on the queries typically, or maybe a couple of seconds on very long queries. Need to do more evaluation. It seems that probably you want queries that produce large results targeting a table or file, not a display, because it seems that there is a considerable amount of time displaying a few 100,000 rows, and what are you going to do, look at them? So that would be a caveat if you were trying to use this in production. Now, we've got about 6 months of data to and from our home network. That's about 82 million rows. That's not much. And as we'll see, that's not what we used for most of the performance tests. We created 6 monthly tables and joined them by union all view. Now, this first run isn't necessarily to demonstrate the feasibility of using Redshift for large amounts of data. It's a sanity check. I want to do something with the data that's small enough so that I can actually get it up and running in a matter of minutes rather than a matter of hours or more. And so we can run some queries against it. And first one we ran was select star from YAF-all, which is the view. Where the protocol was 50, that's VPNs into our system. And the continued flag is true or continuation flag equals true. So these are parts of long-running VPN sessions. That got us 32,000 rows in 48.78 seconds, and then I did it 3 more times to get things. Now, one of the things that bothers me a little bit is there's a fairly high degree of variation. And I think this is probably an artifact of the use of virtual machines in the cloud, that I'm seeing some resource contention. It isn't just me that is on those machines, even though it looks that way. I don't like virtual machines. I want something I can hold in my hand. But this is the way the world works. So now if we select just a few fields, SIP, DIP, start time and duration, and packets and bytes from that, we get the same 32,502 rows, but we get them in 16 seconds. And the subsequent ones went down to 10 8-second range. Now, I have a machine which is an 8-core, fairly fast Intel processor with 16 gigs of RAM that I have my Silk repository on that I used for getting this. So I ran the same query there effectively. And the first time it took 81 seconds, and the subsequent times it took about 16. Now, I know in this particular case that the data is on a 7,200 RPM rotating disk, but this machine has more than enough RAM to hold it all. So essentially what happened was all of the data, all 82 million records were cached after that first 80-second run. And the 16 seconds essentially reflects a single-core, single-threaded application of Silk in that machine. I believe that machine is faster than the DW2 large, but I don't know for sure. It's really hard to compare those things. So all this does is demonstrate that we can do something here. It also gives us a pretty good notion that select star is not a good thing to do, even on a database that only has about 40 columns or so. Because we expanded all the TCP flags, we have 36 columns of TCP flags in that database. And if you are used to doing effectively select star, getting all of the Silk records, and then running subsequent queries on those, it will actually pay you here to select only the fields that you're going to use in the subsequent queries, not all of them, because of the cost of reconstituting the whole record. Different mindset, but it's pretty good. The data used about 5% of the disk on a one-node instance, and this query doesn't really use the index. Getting a lot of data is hard, so I built a data multiplier that basically takes a set of data and gives you 20 records out for each input, or gives you 400 records out for each input. And that gave me a set with 1.6 billion and 33 billion records. Essentially what we do is we take everything in the original record and put it over in the replica, except the source or destination IP addresses that are in our local network are translated on a per replica basis up into a /22 that's in an area where we had no data at all. So if you have a query that involves one of the addresses that's in our original network, you are finding exactly the same records you found before, but they are in 19 noise records per record you're finding, or 399 noise records per record you're finding. So this will stress some of the queries for these small types of queries without changing the results if things work. We also took advantage of the fact that the redshift timestamps are microsecond level, and so we stuffed the replica number in the 3 low-order digits of the microsecond part of the timestamp. So if you did pull one of those out, you would know which replica you had pulled. Say data against our original block produces exactly the same results as working with the original data, but more data has to be processed to find it, which is what we want to do when we're looking at scalings. So the first thing we did with the 20x data is we asked our original query. And instead of taking 10 seconds, it took about 150 seconds. And it returned 650,000 records. Wrong answer. This is better than 20x the original time, but it's not anywhere near what the 5x increase in performance we would expect for having gone to 4 times as many cores and 20 times as many data, 20 times as much data. And I got a feeling that rendering the values and transmitting the data were a major contributor to that timing, but I'm not actually sure, and since I didn't intend to ask the question, we didn't look at that any further. When we add the input data range into the original query so that we only find the records we found in the original query, we get the same 32,502 records in 28, 27, 26 seconds, which is less than 3 times the single node time. So this says we're getting better than linear scaling, because we would expect about 5x if things were scaling linearly. I don't think the single node is a good base case for anything but the sanity checks, so that's probably not a bad thing. The other thing you'll notice here is that sips and dips are these god-awful integers. And that is because Redshift's version of SQL doesn't have an IP type. And so we can't ask the question in any way. That says if you're going to use this for production, you want a front end that will translate things in and out into things that the analyst can understand. I spent a lot of time on one of these IP to integer websites, cutting and pasting IP addresses and integers just to get what I needed to put into that. Going up to 400x, the results are even better. Linear scaling would be 25 times the base time or 5 times the 20x time. Running the same query as the 20x case, we got the results in 143 seconds, was about 4.5 times the 20x time, so that's better than the 5x that we expected. Loading the data required about 6 hours, loading it in 1 month chunks. Now what I had done is I'd set up my replicator to produce files that were 1 gigabyte each, and these are text files because, like Spark, it doesn't very well do binary. So we have to put the stuff in as text form, even though internally integers are stored as binary and compressed. But the interface is unfortunately a text interface. So I was aiming at keeping the files under the 100 megabyte recommended value for uploading files at one time into Redshift. I got better compression than I expected, so many of these files were down in the 30 to 50 megabyte range. But 1 gig files went into 20 or 30 meg files that then had to be uploaded using a manifest file. It required, say, about 6 hours to load the data in 1 month chunks. I did 1 month of it as daily loads, and that took 1 to 2 minutes per day, which was a little bit better than the monthly files. But one of the things that happened when we loaded all the data in one big chunk is the memory usage during the load went way up. And I think what was happening was that we were using most of the available disks to sort the data on input, because it's not sorted when it gets there, and Redshift sorts it on the way in. So putting huge chunks in, we get an efficient, fast sort, faster than the multiple sorts that it required to do the 1 day. But doing the 1 days, you didn't see a glitch in the memory usage as you went up. Now, I hit that when I tried to load the 20x data into the 1 node instance, and I ran out of disk after about the 3rd month. So that's not going to be a problem if you're doing incremental updates and loading the data by an hour as an hour becomes available. You just won't see that. But if you try to load it in a yearly chunk, you may run out of memory, even though it will fit once it's loaded. Restore takes about an hour. Saves go in seconds. But Redshift is doing incremental snapshots in the background, and that may also be affecting some of the performance figures that you see in there. And so I think what happens when you say, give me a static snapshot, I'm shutting this thing down, it says, oh, it'll take me 3 seconds to do the differences from the last snapshot I did and merge them together. So snapshot, boom, you're done. When you say restore, it's reading the whole snapshot. The 300x snapshot is 1.2 terabytes, including all of the compression. Now, the reason why I asked the IP set question is that's a common thing we do. And since we know that the answer with these kinds of things is to do some sort of a join, that's what I did. And I created a table with the IPs. I was in a very small table. There were only 7 IPs in it, so it's not a good performance example here. But we basically got the subset of all of the VPN addresses that were above 77.000, and we selected out a subset of the addresses. That gave us the 7 addresses we wanted. We then selected out the things that could possibly match. That gave us 16,000 rows in about 2 minutes out of the 33 billion records. And then we joined those, and that gave us 104 records in about 0.6 seconds once we had gotten the subset of data that we needed to use. Took about 2 minutes to locate 104 records, specific records in that 33 billion, another minute or so for the preliminaries. But the interesting thing is, if you expanded that set into IP equals, IP equals, or IP equals, or IP equals, it ran the whole thing in 1 minute 39 seconds. So that says for small sets, enumerate them. I need to try to run this with a set of a few thousand records, and that means I'm going to have to be searching over in the outside address part to get that many records, because I only have 1,000 addresses in my internal network, and we'll have to see. I'm willing to bet that the thing that is going to kill these kinds of approaches, unless we can figure out an efficient way to do it, are going to be searches for arbitrary sets. And I'd love to be proven wrong on that, because that is the bread and butter of an awful lot of what we do. Okay, the index doesn't seem to be a really effective query time reduction mechanism, which surprises me. The sample queries were not time limited, but time limiting them had at most a linear effect. We're still searching those tables. The primary key as hour is probably limiting the utility of the other keys in terms of the sort order. So I don't know. A volume summary, flows, packets, and bytes by hour for September, which is 7.9 billion rows, took about 80 seconds. And that's requiring to read all of the data in that small section and work on it. Restructuring to the /22 of interest takes about 8 seconds for the 7.3 million rows that are there. If we include protocol 50 in there, we drop to 7 seconds for 2.5K rows. Using the /22 as the destination IP, which is not indexed, gives 12 seconds for about 12 million rows in there. So the improvement of having the IP address as part of the index is about 50%, but it's small in that. I think performance is probably a function of the number of columns you're inspecting and the number of columns you extract. I mean, that's what the columnar part of it would indicate as a good possibility. So the single index requires some choice after the start order, and by SIP was real easy on that. But the dips are now more or less randomly spread out. So if you do a query involving dips, you're going to look at every record for the hour in question. You definitely want to time limit queries if you can for this. If we maintained a monthly inventory indexed by IP address, we'd have 744 columns. We could do similar inventories for ports and protocols and things like that, and just say, where are these things? And a query for the key gets all the activity for the month, so that may get you a lot of stuff in there. You can encode all of that, approximate volumes. I mean, log scale volumes are probably good. You want to know if there are fewer than 3 or 4 packets, somewhere in the 5 to 10 packet range. You know, it's a 1, 2, 3 many type of compression of that. That'll fit in a 64-bit number, so there are lots of ways you can do this. It's a warehouse problem for static months. It's a regular DBNS problem for the current month, since you're adding hours on every hour into the thing, and you're mucking up the IP addresses because that's your key in there. Politics, customer data in the cloud. I wouldn't want to do that, but I'm paranoid. And most of our customers don't seem to be unhappy with the idea that their flow data is going to be in the cloud somewhere. Loss of control over the environment and security concerns. Apparently they don't care. If they don't care, why should I care? Making maintenance, service, and so on somebody else's problem is a good trade of money for relief, and it seems to be something done. The not invented here problem, that's my problem. Sometimes you have to learn to live with others' decisions. The technical interface, the interface sucks, okay? It is claimed to be almost like Postgres SQL, but it's not quite exactly, because everything you want is in the unsupported list, like IP addresses, regular expression matches, and things like that are not there. Input and output data are effectively text. So if you were going to run YAF into Redshift, you would want something early on that looked like RW cut and figured out the other things you wanted. On the plus side, many of the Silk style reports, top ends, volume distributions, all of that sort of stuff can be generated by a single SQL query, and that's nice because you can arbitrarily change those things without doing any C programming. Just write a new query and away it goes. 9,900 tables per database seems like a lot, but if you did a table per hour per sensor per flow type, you're out of tables in a month or two. So that doesn't help. The data is sorted, and I say that probably accounted for my disk explosion. If inserting replaces records, you pay to clean up the table vacuuming. If you have to rescale the table, that's a very expensive operation. If you over-provisioned, you pay a lot more for the disk space or cores you're not using. So probably the trick is to keep all of your original data somewhere else like S3, and if you start to run up against the limitations of the cluster you're using for production and you can go to a larger cluster, you start by provisioning the larger cluster, putting all of the data from S3 into it, and then decommissioning the smaller cluster so that you don't have a loss of service time in between them. Because reformatting and recommissioning a given cluster to a new size can take it out of commission for anywhere from hours to days in a big cluster. The single index means that some fields will require brute force search. Hourly keys work the same way Centaur hourly files do for that. You get some advantage from the having a key order, but who knows? So it may be a viable way to store flow data. But one of the things I'd like to know for doing this especially, I'd like to know this anyhow, is what are the query styles that are used? We've made a couple of abortive attempts to collect actual queries so that we could do this. Analysts don't like it for various reasons. Some of the information in them is sensitive. I don't need that. What I want to know is the features. I want to know the sizes of lists and sets. I want to know how big the time ranges are. I want to know when IP sets and wildcards are used, what they imply, not what they actually were. Similar for use of CIDRs and sets. If we could get that kind of information, we could probably build a much more effective repository by targeting it towards the way things are done, tracking that continuously, and if they drift, looking at reprovisioning or reorganizing to make that happen and see what happens. Redshift uses uniform distribution. So, if you have n cores or n nodes in your cluster, every nth record appears on a different core. That keeps them balanced. This is one of the problems with the hourly files by sensor in Centaur is a lot of the nodes in the system are not used for a given query. And probably a lot of the nodes are hit very frequently when some hot topic comes up. This spreads everything evenly, and I think may have a performance advantage. If we had better indexing on these things, we might be able to answer a lot of queries in the negative from the indices. And that might help. If we really need select star, columnar storage is probably not a good thing, but we could probably find representations that would admit more efficient compression, and that could be a win. The other thing is that this data has a tapering access pattern with time. We don't go back and look at the flow data from 2000 very often. We look at the flow data from the last month or so a lot. So you might want to have a dozen copies of that data, and then maybe 3 copies back to 6 months, and then maybe one copy beyond that, depending on the access patterns. That would mean that the bottlenecks for the analysts wouldn't be everybody hitting the most recent data in the most recent place. I think those things are independent of this, but who knows? Okay, and here's the obligatory FlowCon slide. When I lived in Canada a few years ago, I became aware of the fact that FlowCon means flake. And so these are cornflakes in this particular case. Questions?
By the fact that your customers were fine with the idea of pushing their flows up into the cloud, because we've gotten a lot of pushback on that idea when we've floated it in various places.
It may be different customers.
In our case, it was mostly, there's a lot of internal flow traffic, which means that the flows would have exposed details of their internal network, and I was wondering if that was so much the case with your customers or not.
All I can say is we've not been seeing this pushback, and there is a mix of internal and external. I can give you another reference point on this. Ron McLeod has presented the last couple of FlowCons. He has a little system that collects flow at the CPU level on Windows machines. And he thought when he built that system that the customers he was going to be selling it to would want it to go to a proprietary or a closed store in their system. Most of them wanted it to go to the cloud so that they didn't have to deal with maintaining that. Your mileage may vary.
I was a bit surprised by your statement that there was a lack of looking for things inside sets. Is that a limitation of Amazon?
The problem is that the relational database model doesn't deal well with sets. Okay, I mean, the thing is, if you look at the way Silk does a set, okay, a set is a bitmap. Mm-hmm. And is the IP of the record I just read in this set is a matter of doing a bit indexing into the set and finding out whether it's a 1 or 0. That's an order linear time, a couple of shifts, and a compare, and an indexing operation. It's very, very fast. The equivalent of that in SQL and other query languages of that type that I know is either a series of specific comparisons. Is it equal to this thing? Is it equal to this thing? Is it equal to this thing? And so on. Not until you reach to the end and find it's not equal to any of them do you drop out of that. So if you've got a set of 1,000 and you blow it up fully, you're going to get 1,000 comparisons for every record you don't select, and on average, say 500 for every record you do select. The alternative, which I experimented with, doing a join, basically you have these two tables, and you have one which has nothing but the IP addresses. And you have the other one which has IP addresses and all the other stuff you're asking for. And what it does is every record that comes in, it has to do effectively the same thing. Look through this other table and see if the IP address that you've put in it is in it. Then if that is the case, it gives you that record out of the join. And it may give you just specific fields. You can at least combine that sort of thing. But it's not a nice thing in that parlance. Now, what you'd really like if you wanted to do sets in a database is you'd like to say where my function of IP address equals true. And my function is a Silk IP set buried in there. And that way you would make a fast comparison in an indexed set for each of those IP addresses rather than a programmed walk through the list and see what's happening. But it's an artifact of the way joins work in these database systems, and joins are probably one of the least efficient operations that you can do, even with query optimization and things like that. This needs more experimentation. There may be a better way, but we've hit this every time we've tried to do flow with sets in any sort of database. If somebody can show me examples that will go really fast for this sort of thing, I will be eternally grateful.
So SQL does have a set query syntax, but I expect it probably just loops through the elements of the set as opposed to...
I think it does. I mean, I think we've tried it on a couple of systems, and just because the language has it doesn't necessarily mean it's implemented efficiently, and everybody warns against doing them.
Thank you.
Yep.
So John, thank you for actually showing us some metrics and benchmarks with your presentation. So as a guy who evaluates architectures often for, data-intensive type applications like flow analytics and PCAP analytics, often people forget about benchmarking things in real-world type of scenarios. So during an attack, you're going to have all your analysts hitting a specific point in time concurrently.
Right.
So did you guys focus at all on any of that and benchmark concurrency of many queries against the same data?
I say this was very preliminary work. I can tell you what what Amazon says about this, though, is that performance drops off linearly with the number of parallel queries.
Yep.
If it drops off no worse than that, it ain't any worse than Centaur is. But I think the answer here is that attacks that we're dealing with are going to have people hitting probably some of the most recent data first. You need to figure out what thresholds typically get hit in attacks like that and arrange to have multiple copies of that data. That can be done transparently. There are load balancers and things like that that will do it. But I think replicating so that we can, say, have 100 analysts hitting it and maybe drop off only by 10 times what it would happen if only one analyst were hitting it, or if one per replica was hitting it, we'd probably be better off.
And then a follow-on, how does it perform while you're loading data? Because a lot of times, we don't evaluate these systems while we're actively loading data. They're in a vacuum. You've already loaded all your data, and now you run queries. But in reality, we're going to be streaming data in, querying it at the same time, and then querying concurrently.
Okay. You're going to have some minor hiccups of that. Again, I'm going on basically on what I've read about what happens. Right. Essentially, you can query while you are adding data, but adding data is effectively a batch operation with this. So I'm probably going to be adding an hourly file, and I'm going to be adding it on to the end of the existing table because I have to keep that sort order, and I can't add the hourly file unlike the way RWPAC works. Since it's not sorting, it can just keep stuffing records on the end. But this, because I'm sorting by my keys, I have to wait until the hour settles, so maybe 30, 35 minutes after the end of the hour, if everything's working right, I can send it in and put it in. I have a feeling this hiccup's going to be a couple of seconds at most, based on what it took me to load an hour here. So what will happen is that until the load is finished, the new data will not be available. But I think it will be sorted. There are probably plenty of resources in the cluster. Eventually, it will be distributed and, bam, added onto the tail of the files that are there. Once that's finished, the readable area of those files will advance to the end of the new data, and it will be available.
Thank you.
But I don't know. You're basically outlining the next series of experiments that we need to do if we're going to get serious about this.
Thank you.
So, okay. So I've seen, we actually have in production probably 20 internet providers, 10 web companies, and about 20 enterprise that have been willing to do flow export and analytics in the cloud. But the requirement that they almost all have, which is something that, I don't know, maybe SCTP, maybe Silk does support, is encryption across the net, which you can argue about whether that's actually adding anything or whether that's the problem. But second, we'd be happy to give you a few hundred of the most popular queries that we see. We looked at Redshift and also Impala and Drill and the other upcoming column stores, and for large-scale flow analytics, said that they weren't. We didn't think they were quite there yet. And actually storing per minute and even per second in RAM and doing the replication, a lot of the things that you're talking about were needed. For Postgres for front end, I can tell you that if you have a good back end system, doing joins that are basically just expanded. We've seen them work super fast, hundreds or thousands of IPs, as long as the query is distributed to the node where the data is, and then it combines back up. Yeah. So in our world, we did a syntactic sugar of essentially the function which basically expands out so that the user doesn't have to enter that in, and also added IP types, because as you mentioned, it's a pain in the butt not to have that. So.
I would be very interested to see what Amazon does on that. I mean, part of the problem is they're selling a service and commodity rather than a development platform, so I'm not able to go in and tweak the way they do it. If their query optimizer will handle that case well, then we win. Otherwise, we have to lean on them. Thank you.